Begin our last speaker, Dmitry Viktorovich Zavadskii.
May I start? Firstly, I must ask, should I use English or the Russian language is more preferable?
Have you English slides?
Yes, I have English slides, but I may communicate in Russian as well. Or maybe I should use English only.
I think you should speak English.
Oh, okay.
You have English slides.
Okay. I would like to tell you some words about measure theory on infinity dimensional spaces. In particular, I will consider shift invariant measures. There is a problem with Lebesgue analogues in infinity dimensional spaces because there is no the direct analog of the Lebesgue measure in infinity dimensional space. So some useful properties should be sacrificed. In my construction, I sacrifice sigma finiteness of the measure, and it causes some struggles with integrable operators on infinity dimensional spaces because of absence of Fubini's theorem. Also, I will tell you some words about semigroups of shift operators and how we may average them. After that, I will talk about representation and application of about the applications of different representations of square integrable functions. So let's start. Let us take a cube K in infinity dimensional space in the space L infinity, and we introduce a product measure lambda in the following way. As a product of one-dimensional Lebesgue measures. Our next step is to extend this measure on shifts of measurable sets. I will write the straight definitions. Okay. We have a measurable set A, and we consider a set H plus V to be measurable as well, where H from L infinity and a set A is measurable. And moreover, we can extend lambda on this kind of sets in the following way. Our next step is to extend lambda on Borel sigma algebra. There is a theorem, measure lambda is well defined, sigma additive and shift invariant on Borel sets in N infinity. But this measure actually is not so appropriate because it is not a sigma finite one. As I said earlier, it may occur some difficulties with Fubini theorem. Next, we consider operator semigroups ATH, which may be defined in the following way. It's simply shifts. Also, it is easy to note that all of them are normed. And we know that an operator semigroup ATH is strongly continuous if and only if H is an element from the L1 space. Our next step is to average semigroups ATH by Gaussian measures. That is why we construct the Gaussian measure, which is concentrated on the L1 space, we construct it like a product measure, but with some specific constants. I think it's actually not a big deal how exactly we do it, so we may move on. We obtain an operator semigroup HT as a result of averaging of previous shift semigroups. HT may be represented like the integral, but this expression has one obstacle. We can't state that this integral is actually a measurable function by x, because our measure is not sigma finite, and we can't apply Fubini theorem directly. That is why we don't know. This expression might be not measurable by x.
But the function you integrate, is it integrable?
Yes, of course.
But then I don't see any problem with sigma finite measures, because any integral function is concentrated on a set of sigma finite measures, and what the problem is.
Yes, but how can we state that this integral is a sigma finite function? Because U belongs to L2 with respect to lambda, and we integrate by...
You say that U is not only in L2, but also in L1, correct?
Why?
Your function U isn't be in L1, it's only in L2, right?
Yes, we consider it to be in the L2 space. It's not necessarily be in L1 as well.
Okay, then it is still concentrated, of course, on a sigma.
Yes, it's concentrated, but we consider this function to be a function from x. Of course, this integral is well defined, but when we start to estimate norm of this integral, we must write another integral over this one. I mean that we must U is integrable, yes. U belongs to L2 by lambda.
But if it is L2, then it's not necessarily in L1. Why not L1? Because the measure is not finite.
Measure is not finite, moreover, it is not a sigma finite one.
But you have no, U is not cylindric, for example, function which depends on finitely many coordinates.
No, it depends on all coordinates. Yes, of course.
So there is no cylindric function?
No cylindric function. U is U simply belongs to L2 and nothing more. So we can't state that this integral function, this internal function is actually measurable by lambda. It may not. Because if lambda is sigma finite, we may say that everything is okay because Fubini theorem is applicable, but this is not this case. So that is why we have some struggles with the definition of this integral, and we have to consider it in some different way. For example, we may define this integral in Petty's sense. It means that we consider a dot product in L2 by lambda, and we obtain a bilinear form, and it is well known that there is only one operator which satisfies this equality, and this operator is considered to be HT. So we define this, it is HT is an operator semigroup which is strongly continuous. Okay, should move next. Yes, and I want to tell you some words about representation, because here we faced struggles with definition, and my goal is to construct some analogs of the L2 spaces which can help us to come up with these struggles in the definition. So we consider the L2 bar space contains of the following objects. A single object in this space is actually a set of pairs M and Fm, which satisfy the following conditions. M must be a countable union of sets with finite measure. F must be in L2 with the restriction L2 of L2 onto M. The third property gives us that actually this object are quite similar to usual functions, and the fourth we have these conditions. We have this condition. It is similar to the analog in the L2 space, and this expression is actually a norm in this space. Our next step is to define an operator E from L2 to L2 row, L2 bar, in the following way. E F equals set of pairs M and restriction F to M. This operator is a linear isometry between the L2 space and the L2 bar space. So these spaces are similar, but they are not equal. Our next goal is to show the difference between these spaces. We consider a set A, which is a product of 2 points, and it is interesting to note that lambda from A is infinity. That is why if we apply usual L2 norm to this function, we obtain infinity. On the other hand, we know that a set A does not contain non-trivial subsets with finite measure. It means the following. If B a subset of A and lambda from B less than infinity, it means that lambda from B equals to 0. It means that if we apply L2 bar norm to this function, we obtain 0, because here we consider only sets M which are countable unions of sets with finite measures. So this example shows us the difference between L2 and L2 bar. I want to say some words about applications of this space. We may consider operator HT bar from L2 to L2 bar in the following way. And here there are no problems with measurability, because M is a finite union of countable sets. So this integral is actually a measurable function of x on M, but not on the whole space L infinity, only on a countable union of sets with a finite measure. And the last result is that HT with a bar equals to HT multiplied by E, when E is Where is it? When E is this operator. So E means almost identity. So these two operators, HT bar and HT, almost the same. And as a result, we construct a method which can help us to come up with absence of measurability in spaces with infinite dimension. So that's all. Thank you for your attention.
So let's pick one again. Все? Олег Георгиевич, какие-нибудь объявления?
Tomorrow the speaker is Professor Yefremova, whose talk we listened. Tomorrow you are speaker. Tomorrow you are chairman. You are chairman. Not in the morning. Not in the morning. So the chairman in the morning will be announced tomorrow morning. But, nevertheless, the important thing that we plan to have this welcome party on Wednesday at 7 o'clock. And tomorrow we have to estimate the size of money which have to pay, which everybody who want to participate have to pay. So, nevertheless, at least my impression that today everything was very interesting. There were many very interesting talks, and I would like to thank all speakers once more. The first, by the way, as everybody knows, the very first speaker tomorrow is Professor Kozlov. Okay. It is very first speaker. And after that, there are many other very interesting speakers. Thank you.
Олег, я уже говорю, что я